All right. Well, let's go ahead and get started. So basically, what this chapter begins, chapter 7 and chapter 8, is a way of doing physics that's quite a bit different from what we've been doing. We've been using Newton's laws and dynamics and kinematics. This is a way that we've discovered you can do physics entirely differently. For instance, with Newton's laws, an object in motion tends to stay in that state of motion unless acted upon by an external force, which actually can be written most succinctly by saying something along the lines of an object will have a constant velocity unless the net external force acting on it is non-zero. So you can already see it's got some vector quantity associated with the first law. Newton's second law says the summation of the forces is equal to mass times acceleration. Again, that's a vector equation. In fact, it says that the acceleration is equal to the net force divided by the mass of the object, and the net force is actually parallel to the acceleration. And then thirdly, for every action, there's equal but opposite reaction, which literally says, hey, if you apply a force A to object B, then that force will be FBA, and the force that it applies to you will be FAB, which is given by the negative of the original force. In other words, it's a vector equation, again, giving you an opposite force. So it turns out there's a way you can do physics largely without vectors. Now, that doesn't mean you completely can get away from vectors, but a lot of the stuff you can do, you can come across it easier. Like in the case of Newton's laws of motion, you normally use Newton's second law of motion. You can figure out the acceleration from F equals ma. Then you can use A in kinematics to determine the final velocity, initial velocity, that kind of stuff. In this new paradigm, you can actually skip the acceleration part, just use scalars, no vectors, and get a final velocity, initial velocity, and then you can work backwards to try to figure out a vector quantity like the actual direction of the final velocity, or the direction of the initial velocity, or the acceleration, or even the forces. So that's where we're going, and it obviously makes it potentially easier. But in order to do so, we first got to introduce this quantity called work. And we want when we bring up a thing like work, or some of the other some of the other terms that we use in physics are supposed to have some bearing, like momentum, on our everyday life uses of words like momentum and stuff like that. So we want those to be similar, but we also want them to be precisely defined so that everybody can agree, hey, this is energy, or hey, this is work, or hey, this is momentum. So first off, I'd make an argument for you regarding, let's say, work and your everyday life experience. If you have to cut a lawn, for instance, let's imagine the scenario is you're going to cut a lawn and you've got two lawnmowers that are equally powerful, but one's, say, twice as heavy as the other, and they're push mowers. Do you think that the work done in the twice as heavy one is the same as the work done when you're using the one that's lighter? Or do you think the one that's heavier would actually require more work?
Heavy's more work.
Yes. So the reason why I'm even saying that is that should give you an idea that at least the bare necessities of the beginning of scientific thinking is coming through, and you're finding that you expect work and force to be thumbs up, meaning if the force required to do the job goes up, you expect the work to go up. That doesn't tell us whether it's, like F squared or F cubed or F to the 1/2 power or whatever. It just tells us that when F goes up, we expect the work to go up. And that makes some sense. So that's one idea we would expect work to have. And I will tell you that, in fact, it does have that. Work, the definition of work does include that. What about, let's say you're trying to cut a yard, and the yard is, let's say, 100 feet wide by 200 feet deep. Okay. you've got a 24-inch lawnmower, let's say 26-inch, so you can easily cut 24 inches. Since the lawnmower has a cutting area of 24 inches, that's essentially 2 feet, and you want to be nice and neat about it, maybe you want to go just north, south, north, south, north, south, north, south, north, south. That would be great, and the lawn will look good. But it will require you, since it's 100 foot wide and your lawnmower can only cut 2 foot at a time, that's going to require 50 trips down and back, down and back, down and back. Okay. So would you consider that job, which is 100-foot by 200-foot yard, or would you consider 100-foot by 100-foot yard to be the one that requires the most work? 100 by 100 or 100 by 200?
100 by 200.
Yeah, 100 by 200. Because what's going to happen is, again, both cases, you're going to have to take a 50-foot, 50 trips forward, and then, one forward and then one backwards, that's 2, one forward, one backwards, that's 4, so on and so forth. But in the first case, the 200-foot case, you're going to have to walk for 200 feet and then turn around. Whereas the second case, you're going to have to walk only 100 feet before you turn around. So with that in mind, we've got an idea that work is not only thumbs up with force, we also think maybe work is thumbs up with distance, meaning the farther you've got to go, the larger the amount of work is. And I will tell you that too is consistent with our physics definition of work. The problem is, and you've probably noticed this if you've ever been a kid that had to cut grass yourself, when you go to cut grass, especially when you're small, a push mower has a handle that's, has got some play in it. And if you're, 6 foot tall or so, you can push the mower handle and everything works just fine. But if you're shorter than that, what happens is you're not quite tall enough to push on the handle right, and you end up doing like this or something crazy. Not only that, your body is actually, and your brain are actually pretty smart, and they realize, hey, this is actually easiest to do when I'm pushing with my arms completely horizontal, as opposed to sometimes when your arms are pushing up, or other times when your arms are pushing down. It turns out that when your arms are actually pushing exactly horizontally, which is parallel to the direction you're going, then you tend to think that it's a little easier to do. And that's actually factual, and it's consistent with our definition of work. In other words, when I go to define work in terms of physics, what I'm going to tell you is that work is directly proportional to force. Not force squared, not force to the 1/2 power, just force. I'll say that work is directly proportional to the distance that you actually applied the force along. And I'll also tell you that it's in fact only dependent on the component of force that happens to be parallel to the distance. Okay. So in other words, if you're pushing a lawnmower horizontally 100 feet, any component of force that you did vertically is just wasted. It's not going to any work whatsoever. In fact, as you saw in dynamics, when we had a force that was actually pushing down and to the right, that actually increased the normal force. And since the friction is directly related to the normal force, that increased the friction force, and therefore it made it even harder on us. So that's sort of our definition. Now, I've just talked about how we could deal with define work without respect of without respect to whether the force is a constant in time or a constant in space, whether the relative direction of the force and the direction is changing as a function of time. I haven't taken any of that into consideration. But I'm going to now, because I'm going to give you a more thorough definition. So what we've found so far, whoa, I accidentally turned my camera on. I did not mean to do that. Just go away, camera. Oh, there you go. Woohoo. Okay, so everybody's looking at this. So what we first found was that work, for some reason, is not wanting me to draw. What we first found is that work. Okay, that's weird. I have no idea why all of a sudden it's not letting me write anything. My pen is on. It's not giving my new normal stuff. All right, there you go. Let's try this now. Okay, I think I got it working now. Sorry about that. So we found that work is directly proportional to force. We found that work was directly proportional to distance. And I even made an argument that work will in fact be equal to, and there's a couple ways you can say it. I can take force as a vector quantity and find the component of it that's parallel to D, the displacement vector, or alternatively, I could take the force and multiply it by the component of D that's parallel to F. What do I mean by that? Well, what I mean is if, for instance, I apply a force, say like this, F, and it's applied over a distance like that. That was supposed to be horizontal, by the way. Let's pretend like I made it better. Okay, and that's my displacement vector. Then there's a couple ways you could look at it. One, you might actually imagine dropping or raising a perpendicular line. Notice that that's perpendicular to D. Then what you get here is a component of F that is actually parallel to D. Okay, so that's what I mean by F parallel times D. Alternatively, I could imagine this F vector continuing on until I could then drop a perpendicular to the F. And in this case, I'd say, okay, well, let's use a different color. I'm going to use green. So in this case, I'll say this is the component of D parallel to the F. Okay, so that's what I mean in there. Now, both of these, you can look at these vectors as if they're separated by an angle theta, and then there becomes a nice mathematical tool that we can use. And that mathematical tool is called the dot product or the scalar product. So I'm going to say dot product, which is also equal to the scalar product. And the reason, anybody want to guess what the reason is that they call it a dot product is the scalar product?
Because you're multiplying vectors.
You're multiplying vectors, and what do you think the answer is going to be? A vector or
A point.
something like that? It's basically going to give us a scalar, which is a number without direction, in other words. That's to be contrasted. Notice I just wrote F dot D. Okay, that's the scalar product. And I wrote in some cases. And the reason why I'm saying that is because this is not true unless F and D are, I'll call it constants, and I'll just say sort of. Okay. In other words, there might be an instant where if you imagine in space in X and Y coordinates, you might have to follow a path like this. And right here, the force might be that direction. And then right here, the force might be that direction. And here, the force might be this direction. And in that case, you've got to dice this little spot of path. You got to cut that up to as small segments as necessary so that you can assume that the force and the direction vector over that is roughly a constant, and then you just sum all those up. So it could get more complicated. But the main thing is we've introduced a dot product, which hopefully you guys covered in trig or in the trigonometric portion of pre-calculus. But not everybody has. Sometimes they never do it. Sometimes they just don't get to it. Sometimes they don't care about it. So that being the case, I'm going to go ahead and show you how to calculate a dot product. So the dot product of two vectors, A and B, it does give a scalar. That's important that you know. It gives a number, not a vector. And one way of calculating it is taking the magnitude of A and multiplying it by the magnitude of B and multiplying that times the cosine of theta. But in order to use this definition, you've got to have accompanying a diagram. So the accompanying diagram for this is that the vectors are tail to tail, and the smallest angle between them when they're tail to tail is the angle theta. Now, we don't have to go through all that trouble of writing A with a vector arrow on top and then a absolute value bar to say the magnitude. So it's actually easier to write it as A times B times the cosine of the angle between them. And I think you can start to see why this definition works. Because if you look up here, how could you get F parallel? What are you going to do to F to get F parallel in that drawing? Assuming you know theta and you know the magnitude of F.
Cosine.
Yeah, you'd write F times the cosine of theta, wouldn't you? So if you take F times the cosine of theta and then multiply that by the length D, then yeah, that's exactly the dot product. Alternatively, you could say, well, D is actually given by, this D parallel is actually given by D cosine theta. So you can see why it works. Now, the good news is, I say the good news, you could actually prove this if you so desired, but you probably don't desire. It turns out you can also write the dot product as the X component of A times the X component of B plus the X component, or excuse me, Y component of A times the Y component of B plus the Z component of A times the Z component of B. And remember, these components are just numbers. They have a sign, they have a positive or negative to them, but they're just numbers. So in other words, it's a scalar product, out pops a scalar, period. No ifs, ands, or buts about that. Okay. So what this is often used for instance, in solid state physics, which is sort of comes under the idea of material science and can be useful, for instance, in mechanical engineering and stuff like that. A lot of times you'll have two vectors, and it's really important that you know the angle between them. So for instance, you could be talking about the lattice structure of, say, aluminum or sodium chloride or something like that. Well, it turns out that atoms / molecules tend to orient themselves in 3 dimensions in very specific ways, such that the potential energy is a minimum. And when you do that, that ends up coming up with different shapes. There's like face-centered cubic and body-centered cubic and all sorts of neat things like that. But if you imagined basically 8 atoms at the corners of a cube, and then put one atom in the center, or one different atom in the center, or one different molecule in the center. And then the 8 could be atoms or molecules as well. That would be a body-centered cubic. And for instance, you might need to know the angle between the body-centered cubic bond with one of the corner atoms and the corner atom with another corner atom. And in order to know that, you need the angle between them. Well, that's where a dot product can come in very helpfully and help you work out the quantum mechanics of it. So that's something that comes up from time to time. And to be honest with you, the more stuff you know about how to manipulate vectors, the easier your life can be. For instance, you can talk about a vector, which I'll call the projection. So let's say the projection of A onto B. Okay, this is a vector. I'm going to call it the projection of A onto B. What I mean is, I would like to know exactly what vector is the same length as the component of A that's parallel to B, but points in the direction of B. Well, I don't memorize this. In fact, I rederive it every time, but I found it infinitely helpful because I can go ahead and take this now and say, well, I know, for instance, if I want the component of A, let's say parallel to B, I can take this line right here and draw that like that. And this will be the component of A parallel to B. So I'd like to know that length. Well, I know that length is A cosine theta, which I can see is this guy and this guy. So I'll just say A dot B. Actually, I should write it in blue since I've already started in blue. I can say this is going to be A dot B. But now I realize, well, wait a second, A dot B also has that B in here, which I really don't care for that much. So I'm going to go ahead and divide that out. Notice that the B, which is in the symbol, that's the one that appears twice as much so far. Now, here's the deal. You also want it to be a vector quantity, and you know that this little projection of A onto B technically should be, let's draw it with, I'm going to draw it with a green vector. So this green vector right here, that is the projection of A onto B. So you see it's parallel to B. So ideally, by taking the dot product of A and B and then dividing out the B, I've now got the length of A, but now I've just got a scalar. So I really, really want a vector. Well, you'd say, well, the vectorness of it, it's got to be parallel to B, so I can just multiply it by B. But if I multiply it by B, you can see now I'm back to the point where it's A times B times cosine theta. So what I'd prefer to do is multiply it by a unit vector parallel to B. And of course, if you ever want a unit vector, all you got to do is take the vector that you want it parallel to and divide it by its own magnitude. So I'm going to say B divided by B. And in fact, that's the final formula. What I'm going to do is I'm going to say the projection of A onto B is A dot B over B squared, all of that times B. And then you'll see, obviously, B occurs a lot more in this formula than A does, but that will, in fact, give me exactly that little green vector. So that I've used that numerous times in engineering classes as well as in physics classes, just because I can quickly derive that without having to memorize the formula. I can quickly derive that, and then I can use it over and over again. One of the processes that you do when you're talking about trying to navigate in space is you have to create a new coordinate system. Your new coordinate system might have, for instance, X pointing the same direction as the ship travels, Y might be to your right, and then Z would be straight up. Well, how do you do that? Well, you've got to take 2 points in space and subtract the coordinates of one point, the last one, the initial one, from the last one, and that'll give you basically the lengths of the components of the vector. And if you actually just put it in front of I hat, J hat, and K hat, you'll have a vector parallel to whatever line you wanted. You can then take another vector in space, and ideally not in the same line as that one. And long as it's not parallel to that one, it will have a component that's perpendicular to that first vector. So if you subtract out the component that's parallel, in other words, you subtract out that projection, you'll get a new vector that's parallel to the first, or excuse me, perpendicular to the first one. So that first vector could have been your x-axis. The second vector might be your y-axis. Now you've got 2 vectors that could basically, because it takes 3 points, it could define a plane. So long as you choose a vector that's not completely in that plane, you could then subtract the component parallel to A, subtract the component that's parallel to B, which was your, say, your x-axis and your y-axis. And now all you have is a vector that's perpendicular to X and Y, and therefore is a new Z direction. So there's all sorts, that's called a Gram-Schmidt process, by the way, but there's all sorts of things you can do with that. So let's imagine for a second, I want to show you how valuable this can be. So I'm going to draw a coordinate system. And in this coordinate system, I'm going to say, that's my Z-axis. That's my y-axis, and this is my x-axis. Okay, so one thing I'm going to do is I'm going to imagine going out 1 unit and then going to the left 1 unit. And then, of course, that puts me right here. Now I'm going to imagine going up 1 unit. And that puts me right here at 1 on the z-axis. And in fact, we can call this vector right here vector A. Okay. Now, I think you can tell that vector A could be written as, remember I told you you can use less than or greater than symbols, and then you don't have to write the I, J, and Ks. So you can see, I think, from this that the X component is 1, the Y component is 1, and the J component, or the K component, is 1 as well. And I suspect you can tell that this angle right here, which I'll call phi, can anybody tell me what I need to take the inverse tangent of to get phi? Now, phi, by the way, happens to be the polar angle from spherical coordinates. So when we've talked about, when I mentioned coordinates before, this is a type of coordinate system where you just use r, the distance from the origin. Then you'd use this angle right here, theta, that's called the azimuthal angle. And that goes from 0 to 2 pi, but it's only in the XY axes. And then you'd use the polar angle. So these are related, but can anybody tell me, remember, tangent is opposite over adjacent. Can anybody tell me what the opposite side of that triangle that you see?
Y over X.
Yeah, you'd want, you definitely want the, well, let me draw it on here. You definitely want this divided by this. So can anybody tell me what the opposite is? How long that is? I'll give you a hint. It's the same as this one.
B.
You see that the X component is 1 unit long and the Y component is also 1 unit long and it's lying in the XY plane. How long is that diagonal going to be? This is 1 unit. This is 1 unit. So what's that red one there? Anybody realize it's square root of 2? In fact, this angle right here has to be 45 degrees because they're 1 and 1. Now we've got that, which is the same thing as the opposite of phi. What about this axis along the Z axis? How long is that side? That's the adjacent side to the angle phi. It's actually marked too, so that might help you.
Could you show me where it is? I can't see.
Yes. Okay. So what I'm trying to figure out is we just figured out the adjacent side was from this dot to this dot. And now, or excuse me, the opposite side was from that black dot to that other black dot. Now take that black dot up there on the Z axis. What I want to know now is how far is it to this black dot at the origin? So in other words, how far along the Z axis is it from the origin to where this red opposite line hits the Z axis? Y'all see that that is 1?
Yeah.
There you go. So phi turns out to be, I think this is 54.375 maybe, or maybe it's 745 or something like that. Let me do inverse tangent. Pull out my calculator. I'm going to do 2 square root, and then I'm going to take the inverse tangent. Whoa. 2 square root. Whoa.
54.7.
Yeah, that's what I was getting. Actually, something happened with my calculator. I don't know what the heck was going on with that. But anyways, 54.736. So one of the things that I claim that's helpful about the dot product is because you have 2 ways of getting it, the one where you multiply like components, and then the one where you multiply A times B times cosine theta, you can use that to find the angle. So what I'm going to do is create a vector that's parallel to the Z axis, call it vector C. No, I'll call that vector B. So I'll call it vector B, and I'll say vector B is in fact equal to 0, 0, 3. Okay. So I can see that 0, 0, 3, that's just basically going to be a vector 3 units long parallel to the Z axis. But based on what we drew, we know that the angle between A and C, or excuse me, A and B should be 57.3736. So let's see if the dot product in fact gives us that. So I'm going to say, first off, that A dot B is equal to, now I'm going to take the X component of A, which is 1, and multiply it by the X component of B, which is 0. Do the same thing with the Y component. And then I'm going to do the same thing with the Z component. So in this case, I just get 3. And the reason part of the reason I'm showing you this is I've had students I teach them the scalar product, the dot product. I tell them it's a scalar product, and then they'll give me this number and they'll say it's 0 I hat plus 0 j hat plus 3 k hat. Okay, that's a vector. You don't do that. That's not a good thing. Okay. Now I can also say that the magnitude of A, which we just call plane A, I think you can see that's 1 squared plus 1 squared plus 1 squared, which is a square root of 3. In other words, Pythagorean theorem doesn't just work with 2 dimensions, it works with 3 dimensions. So if I do x component squared plus y component squared plus z component squared, add them all up, take the square root, then I get the component, then I get the actual magnitude. I think you can also see that the magnitude of B, anybody want to guess what the magnitude of B is?
Where is it on the screen?
It'll be 3. It'll be 3.
Yeah, it'd be 3, right? So the magnitude of that one's 3 as well. So what I can do is I can say A dot B, which is equal to A times B times cosine theta. That means it's going to be the square root of 3 times 3 times the cosine. We call that angle phi, so I'm going to have to call it phi. And that is all equal to the dot product, which we already computed was 3. So now, if I was right about my ability to use the cross product to figure out angles, then phi should be given by the inverse cosine of, notice the 3's cancel out, 1 over the square root of 3. Well, that turned out terribly. And lo and behold, you do get that that is 54.736. All right, who can give me vector C? I'm going to open this up a little bit. Look at this drawing again, and let's call this vector C. Vector C is going to go from the origin to this point right here. Can anybody tell me what vector C is, what its x component, y component, and z components are?
One, 1, 0.
Exactly. So can anybody tell me what they think the angle between A and C is?
Square root of 2.
You're thinking that the actual magnitude, you're right at that, but what I'm asking about is
I meant 45. Yeah, 45.
okay. Oh yes, that would be between here and here, but I want to know the angle between here and here. We just found this angle, the phi was 54.375. That's what that top angle phi is. So I'm asking now, what's this angle? That one's not 45. That the one in the XY plane is 45 though.
Are you trying to imply that they're the same angle
No.
as phi?
Yeah, so you do know that the angle between vector C and the Z axis, y'all know that's 90 degrees, right?
Yeah.
Okay. So how is phi and alpha related?
Ninety.
There you go. That's what I was shooting for. So now you know alpha should be equal to what? About let's say 30 gets me up to 84, and then 35 gets me up to 89. So I would say alpha should be on the order of 35.264. What? 0.264 degrees roughly. I think that's what alpha should be. So we can see that the dot product, of course, of C and B, or excuse me, I don't want this dot product of C and B. They're obviously 90, so it gives you 0. But the dot product of C and A, I think y'all all can see that that dot product is what? And actually, let me blow this up. Erase
110.
exactly, because they're the way you're going to multiply them. You're obviously going to get, yeah, you're saying everything right there. So A dot C is equal to 1 times 1 for the X component, so that's 1, plus 1 times 1 for the Y components, so that's 1 again, plus 1 times 0 for the Z components. So this just gives me 2 for A dot C. I think you can guess that the magnitude of, well, you already know the magnitude of A is the square root of 3. And the magnitude of C, I suspect y'all can tell is 1 squared plus 1 squared, take the square root, so that's the square root of 2. So A dot C, I keep wanting to write a B there, is actually equal to the square root of 3 times the square root of 2 times the cosine of alpha. But that, of course, equals 2. So I think you can see that alpha will, in fact, be the inverse cosine of 2 over root 6. Now I'm going to do that calculation. 2, and then I'll do 6 square root. I divide 2 by the square root of 6. That gives me 0.816. Now I'm going to take the inverse tangent of that. Excuse me, inverse cosine of that. And that gives me 35.264. Which is exactly what we predicted. Okay. So sorry about going in all those different ways. I just wanted to show you how to do dot products. That is something you should be able to do at the drop of a hat. We use them, I think, as you can tell here in physics, to find components that are parallel between two vectors. So for instance, if you have a vector A and a vector B, if you want the component of A parallel to B, A dot B is going to be related to that. You just got to divide out the B. That's why what I showed you with that projection formula that I gave you. Okay. We also use another product called the cross product, which is also called the vector product. And that one allows us to pick off components that are perpendicular to each other. In other words, if that's what matters to you, you know, the component of force that's perpendicular to the distance, then that would be given by a cross product. And we'll learn that more next semester. I think we might come on. Yeah, that's right. We cover it in torque too. So I'll show you it again then. But right now we're just occupied with that. Now, I want to generalize that definition of work. And I'm going to say work is actually equal to, remember I told you in the case of like a curving path like that, you want to cut it up so small that each little small section is just a straight dot product of F and C, because that part of the path is straight, that part of the force is constant, that small of an area of the force is constant, the angles are constant. And then by dividing it up that way and adding up the individual parts, you can get the whole process. That's done by integrating all that stuff. So now I'm going to tell you that that integral is in fact the integral of f dot dl, where dl is a line segment, a differential segment of the line. This is, and it's not going to matter too much this semester, but next semester you'll fall into a pit if if you don't realize this. But this is technically a line or path integral. Now, the places I've been as a student or a teacher, we've never gotten to that section in Calc 3. So this is another instance where you're learning your mathematics from your physics or engineering instructor. In principle, if you go far enough in Calc 3, or your instructor does, then they will not only cover multivariable calculus, they'll actually give you a generalized chain rule for not only f being something other than a function of x, for instance, f being a function of x, y, and z, but also not only that, you could have a multi-valued function where you're saying like f has a x component, a y component, and a z component. And in fact, each of those are dependent on, let's say, x, y, z, w, u, v, and t. So a lot of classes actually get to that particular portion of the chain rule, the generalized chain rule in Calc 3, but hardly ever do they get to surface integrals and line integrals. That's what this is a line integral, and there's a very specific process. It's not that complicated. And the good news is most of the time you can integrate it without even realizing it's a line integral and still get the right answer. Okay. So that's really what work is. We will cover that in much more detail in the 242 class. I will show you a couple integrals with that this semester, but it's really not going to be that big a deal for you. So let's start off by solving a problem. The problem I'm going to solve is this one. Let's go ahead and I'm going to change the colors a little bit. What I'm going to do is imagine a box that I'd like to slide across a floor. Okay. This box has a mass of 20 point, has a mass of 20.0 kilograms. And I plan to pull it from here to here, 40 meters away. I plan on doing so via a vector force of, let's say, 220.0 newtons at 37.0 degrees. And this is the magnitude of the force. What I am going to say is that there is a static coefficient of friction, and therefore the kinetic friction is mu kinetic times F normal. Okay. So if I draw my free body diagram so I can get my equations for X and Y and stuff of that sort. There's X, there's Y, okay? What I will see is I have a mass right here of 20.0 kilograms. I have a force of 220.0 newtons at 37 degrees. Let me move this 220 kilograms to somewhere else. Or excuse me, this 20 kilograms to somewhere else. So I'm going to say this angle right here is 37 degrees. I have also acting on it in the negative direction. I have kinetic friction, and have acting on it in the positive direction, which I shall label as green, a normal force Fn. Okay. Now I think you can see that, in fact, I can break this force up into that component and this component. This one will be 220.0 newtons times the cosine of 37 degrees. And this one will be 220.0 newtons times the sine of 37 degrees. And technically I'm saying 37.0, even though I didn't write it down. So let me just stick it in there so we can remember, at least we got 3 sig figs on everything. So I'm going to try using my calculator on my computer. It looks like 220 times cosine of whoop. Okay, yeah, I forgot this calculator does that backwards. So I'm going to do 37 cosine, that's essentially 0.8, times 220. That gives me 175.7. And then I'm going to say clear that, and I'll do 37 sine, and that gives me essentially 0.6 times 220. That's going to give me 132.4 newtons. Okay, that's 4 sig figs and 3 sig figs. So really that's 1 extra sig fig, and that's 1 extra sig fig there. Everybody understand what we did now? Now the summation of the forces in the y direction has got to equal mass times acceleration in the y direction. Now in this case, I'm just trying to slide a crate across the floor of Home Depot, say, right? So what do you expect the acceleration in the y direction to be? Anyone? So we're not expecting it to have any velocity in the upward direction or the downward direction. And in fact, you never expect it to. So it's not only that the velocity is 0, it's that the velocity is 0, and then the velocity is 0, and then the velocity is still 0. Because you can, even with a velocity equal to 0, you can have a non-zero acceleration. That's exactly what happens when you're swinging on a swing set and you get to the top of the height of your swing. At that point, you come to a stop for a split second, but your acceleration is still 9.8 meters per second every second downward. So in this case, we're actually going to have the acceleration is equal to 0, and we see all the forces acting on it, which one I didn't include here was this guy. That's the weight, which equals mg, which is 196.0 newtons. That's 1 extra sig fig 2. Okay. So the summation of forces in the y direction gives me F normal minus 196.0 newtons plus 132.4 newtons is equal to 0. So now I figure out that the normal force is in fact 196 minus 132.4. And that gives me 63.6. Now, technically, because this is a subtraction problem, this single decimal place is actually not a sig fig. So we've actually lost sig figs, and we only have 2 sig figs on the normal force now. Now, one thing I didn't give you in the problem, but I meant to, was that mu k is 0.200. Okay. So now that I have that, I can start working stuff out. Now, what am I trying to solve for? What I want to know is what is the work done by the force F. I also would like to know what is the work done by the normal force. And finally, I'd like to know what is the work done by friction. So that's what I'm trying to solve here. Okay. In order for me to get the friction force, I had to have the normal force, which is why I had to do a free body diagram and all that good stuff. Otherwise, we could often get away with no vectors. That's sort of the point of the work and energy idea. Now that I have that, I can see that the friction force, which is equal to mu kinetic times the normal force, is actually about 12.72 newtons. Okay, because basically I'm going to divide it by 10 and then multiply by 2. So if I divide 63.6 by 10, that becomes 6.36, and then I multiply that by 2, that becomes 12.72. So that's how I knew that. Now, if I want to calculate the work, in this case, remember earlier I said not true unless F and D are constant, sort of. So this is a case where the angle of the forces nor the direction or any of that stuff is changing. So just dot products is sufficient. I don't have to do the integral stuff. So that's why I'm able to do that. So let's start off with part A. Part A, what is the work done by the force? Well, we defined it earlier as F parallel times D. Well, since I actually worked out the components of the force F, which by the way was this force, since I actually worked out those components, I don't have to actually use any cosine or anything like that. I could realize that F and the displacement vector D, which is essentially this black line that I've gotten intercepted by the 40.0 meters, I could just do 220 newtons times 40 meters times cosine of 30, and that would give me the exact same result. But I'm not doing it that way. I'm just going to use what I told you works earlier, which was the component of F that is actually parallel to the displacement. So I'm going to say this is in fact equal to 175.7 newtons times, in this case, it's 40.0 meters. Now, technically, these two vectors are in fact parallel, so I could write cosine of 0, but there's really no reason to. And what I'm going to have is, if I clear this, I say 175.7. That was, yeah, times 40. That gives me 7,028. Now, remember, technically, I only had 3 sig figs in the 40 meters and in the other one. So technically, this should be 7.03 times 10 to the third. And that should be Newton meters. But the Newton meter is defined to be a joule. So let me make this a little better. Get rid of that too. So a Newton times a meter is defined to be a joule. I'm going to say if I had to put this in the proper number of sig figs, it'd be 7.03 times 10 to the third joules. Now, just for some conceptual idea of what a joule is, I will tell you that a joule is about as much work as it takes to lift a nice, juicy, red, delicious apple off of the floor and put it on top of a, say, kitchen table. That's about 1 joule of work. So in fact, by pulling this 20-kilogram block against friction, I'm doing the equivalent of lifting 7,028 red, delicious apples off the ground and putting them on a kitchen table. So that's one of the forces, one of the works. So again, 1 Newton meter is defined to be 1 joule. That's actually named after a family in Great Britain. There used to be, might still be a beer called Jowls that was made by their family. Their family was, they did a lot of stuff in the past, but one of the things was brewing. Another thing was they would basically build cannons and all sorts of cool stuff. So they're the ones that actually gave us the mechanical equivalent of heat by saying that 1 joule is equal to 4.184 calories. Or excuse me, 1 calorie is equal to 4.184 joules or whichever it is. Now let's do part B, which is the work done by the normal force. So remember, the dot product is what we're using, but the dot product has to come with that little drawing here. So it's A times B times the cosine of the angle between them when they're tail to tail. So if I want to calculate B, the work done by the normal force, then what I have to do is take the normal force, which we found was 63.6 newtons. And remember, that's 1 extra sig fig. And I'm going to multiply that by 40.0 meters. But I noticed that the vector Fn is parallel to the y-axis and the vector D is parallel to the x-axis. So the angle between them is 90 degrees. And does anybody know what the cosine of 90 is?
One.
Close. The cosine
Zero.
of 90 is 0. There you go. The stupid sine and cosine, get them all mixed up, right? So that's the work done by the normal force. And that's actually that's a big concept in physics, or at least it's a concept you should know. Basically, the work done by any force that acts parallel, or excuse me, perpendicular to the actual direction of travel is always going to be 0. Another fundamental concept is getting ready to come up with part C here. So part C, I want to calculate the work done by friction. So the work done by friction, F sub K, is in fact the friction force, which we found was 12 point, whoa, I don't know why I'm crossing my 2 like that, 12.72 newtons, which really should only be 3 sig figs. Actually, since the normal force is only 2, it should only have 2 sig figs. So let's fix that. So it's 12.72 newtons times the distance, which is 40.0 meters. Now, can anybody tell me what the angle is between the friction vector and the D vector? Remember, they got to be tail to tail.
Zero.
Almost. So remember, the normal, the D vector points from left to right, whereas the friction force points from right to left. So they're actually 180 degrees, not 0 degrees. And that 180 makes all the difference because the cosine of 0 is 1, whereas the cosine of 180 brings in that
Negative
other
one.
concept. Yeah, it's -1. So in fact, we get 508.8. And in this case, it's actually supposed to only be 2 sig figs. So joules is the work done by friction, and it's negative. Okay. So that too is another concept that we need to understand, is if you've got a force that is applied to something while it's moving in space, the work done by that force is going to be negative if that force is basically anti-parallel. In other words, if the force points to the left, but the object's ultimately going to the right, then you know that's going to be a negative amount of work done. And that's what happened here. Me applying a force of 220 newtons at 37 degrees was more than sufficient to overcome the friction force. So I won and pulled it to the right, and the friction force was, working on me and making it harder for me to move. But still, I got to ultimately move to the right, whereas the friction force was pulling to the left, and therefore came up negative. Any questions on that? All right, so there's a couple other things we can do. There turns out to be a law called Hooke's law. Now, this is Robert Hooke, one of the nemesis of Isaac Newton. He was the one that I told you had a bit of a short person's complex. And Newton said, if I have seen further than others, only because I stood on the shoulders of giants. That was the guy he was trying to insult with that. But Hooke was a good scientist. I mean, not many people could be compared to Newton. So, God forbid poor Hooke be a good scientist at the same time. But what Hooke found was that when you apply a force F to an object to try to compress it, or apply a force F to an object to try to stretch it, the amount of stretch that you get is directly proportional to the force. And you'd say F is equal to KX. Or if you're working in terms of vectors, you might even call this F is equal to negative KX. And the reason being is if you actually are pulling, say, on a rod, you've got one end of a rod is sitting in a vise that's very connected to something very heavy or immovable. And then you're pulling the other end of the rod to try to stretch it. The force the rod is applying to you is in the exact opposite direction of the stretch. That's why the negative's there. Okay. So if you're talking about the force the object is applying to the puller or pusher, then F is equal to negative KX. So I'll write this as force applied applied to the compressor. I'll say compressing person, or to the stretching person. In other words, if the person's trying to stretch it or compress it, then the force that's negative will be acting in the opposite direction. Okay. So that's called Hooke's law. And it's really hard to see with, 2x4s and iron rods and steel rods and aluminum rods and stuff like that. But it's not that hard to see when you actually work with a spring, which is part of the reason that we work with strings a lot. That and the fact that the potential energy that comes from this, which you can also relate to the work done, is actually the same as the force near any force near an equilibrium point. So what I'm going to do is I'm going to calculate the work done by stretching a spring. So what I'm going to do is I'm going to imagine here's a wall and a floor. Here's a spring, a mass on a spring. And right now it's at equilibrium. what I'm going to do is imagine an x-axis and a y-axis like that. And I'm talking about the work done by me. So I'll write this me is equal to, now what I want to do is apply a force just big enough to stretch the spring, not enough to give it an actual velocity. In other words, an acceleration that leads to a velocity. So I just want to barely equate the force that I'm applying to the force that Hooke's law tells us. So Hooke's law says that when I apply a force to the right, the spring is going to fight back with a force to the left. I want to apply that size force, but to the right. So I'm going to say my force is going to be K times X, where I'll write it this way. X equals 0 at equilibrium. Oops. I'll just call it that. Okay. So when I do that, I'm going to say F equals KX. I'm pulling that in the I hat direction. Excuse me. I changed colors by accident. That force is in the positive I hat direction because that's the force that I applied. The spring is pulling back in the negative. Now the DL is actually DX I hat. So when you're actually doing a line integral, you either have to let the DL point in the direction that you're integrating and going, or you have to let the range of integration dictate it. Whichever one you choose, that's fine, but the other one's got to go in the positive coordinate direction. So I'm going to choose my DX as pointing in the direction of the line integral. In other words, I'm integrating from left to right, and therefore DL points to the right, and therefore I'm letting my DL, which is DX I hat, dictate that. That's part of the idea of this being a line integral. Well, as I told you in the first semester, it's not going to matter too much because you'll still get right answers, even not knowing it's a line integral. So you do this anyways and get the same answer. You just wouldn't go through the process of thinking about it. Now, since I've chosen DL to point the direction I'm integrating, I'm just going to go from small coordinate to large coordinate on my range of integration. And that is from X equals 0 to just plain X, which you can see is exactly the same direction as DX is. So that's why I said it really almost never matters. So what I'm going to get is the integral from 0 to X of KX DX, and then I hat dot I hat. We just learned about dot products. Can anybody guess what I hat dot I hat would be?
I hat squared.
In some sense, yes, but think in terms of this version right here. Let me get my stuff back here. Let me change colors too. Think of this version of the equation for A dot B. So what do you think the magnitude of I hat is? Everybody see the pink arrow I just drew? And what we have is
1.
exactly, the hats mean their unit vectors, so their length is 1. So I've got 1 times 1. Anybody want to guess what the angle between I hat and I hat is? They're identical vectors, so the angle between them is
0.
exactly. And of course, the cosine of 0 is 1. So the whole thing just equals 1. And I get 1/2 kx squared. And you can think of this as potential energy stored in a spring. And that's if the spring has been compressed or stretched by an amount X. So that's one way of thinking about what I just wrote, 1/2 kx squared, stored in spring. But you can also think about it as R as the work done to stretch or compress the spring by X. In other words, if I compressed it an amount X, then or stretched it by an amount X, then the work done in doing so would be work equals 1/2 kx squared. So I'm going to say work equals potential energy equals 1/2 kx squared. And I'm going to box it all off with this red one. And that's how you deal with a variable force. So now you've seen when the force is actually a function of position, you do have to do the integral. We just ran out of time. I will tell you that next time I will cover the work energy theorem. I've already put videos up for you to look at so you can learn that on your own as well. So the work energy theorem, we're going to cover next time. We're going to cover potential energy. And we're going to cover kinetic energy. And we're going to cover conservation of energy. So that's it. You folks are free to go. Thanks for coming, and I'll wait for the last person to leave.
You mind showing the last slide?
Yes. Let me finish writing this up real quick. So you want to see this slide?
Thank you.
By the way, Kamna, I got that
Yes.
message you sent me about the 2R being the diameter. Yeah, I think you're right. It was supposed to be 2R is the new radius, not the new diameter.
Exactly.
Sorry
Because
about
I took that for, I use it for the diameter, and every time I calculated it, it wasn't given the right answer.
right.
And I finally,
Yeah, sometimes they just make typos and they can make a big difference between the answer being right and wrong.
yeah.
All right. You guys are free to go. Like I said, let me know if there's anything I can do to help you. I'm here. Remember, the final will be on the 15th when we return. You want to make sure you can either get your browser to run Canvas test, Respondus lockdown browser, and Respondus monitor, and that you have a Wi-Fi camera that can be used to show your work area, your face, along with a photo ID, government issued photo ID, and each side of any blank paper or equation sheets you might have. If you can't get all that stuff done with your computer, then we'll just have to set you up at testing center, and that's fine too. And they don't charge you anything to do it if you go to a TCC campus. Can I help anybody with anything? Jared, James, Taylor?
I have a quick question.
Yes.
I'm currently changing majors and I need to withdraw from this course. How would I go about that process?
You supposedly have an advisor that can do that for you, or that can tell you where to get the forms and stuff like that. But you can also contact the registrar, and the registrar's office will tell you where the form is, and you just submit it. And just don't forget to do it, because what'll happen is if you don't fill out the document and go through the process, I might not notice till sometime later that you're there, and then I end up doing it, and I'll drop you, and it'll be so late that you end up getting an F even though you dropped early. So just make sure you follow that process.
Okay, I'm in the process of contacting my advisor.
Yeah, if you know your
Thank
advisor
you.
to do that, the help desk can also work if you can't get a hold of your advisor.
Thank you.
No problems. I hope you decide to stay, but I understand if not. See you, Alvin.
See.
Anyone else? All right, well, I'm going to call it a day. I'm assuming Taylor, Alex, Carter.
How many question is gonna be on the?
My midterms normally on the
Midterm.
order of 20, 25 questions. I try to give a lot of what I think are real chucker questions. So that we don't have one of those scenarios where if you just miss one question, you're going to get an 80. So I try to do like 20 to 25 questions, but a buttload of them are really easy. And then a couple are hard.
Okay,
Okay,
thank you.
no problem. Have a good one.
You too.
It looks like no one else has anything to say. Taylor, oh, gotcha. Taylor, I'm reading your text message now or your chat message. Yes, that's, oh yeah, I did talk about that already. Yes, Kevin asked a question about will we be given points X, Y, Z. In general, you can always make a vector if you have like if you want a vector parallel to the line connecting 2 points, you can take the X, Y, Z of the 2 points and take the vector where you want the head to be, take that as the first coordinates, and you subtract from those X, Y's, and Z's the X, Y, and Z of the other point, and that'll always give you the vector components. It'll still look like an ordered triple, but if you change the ordered triple from thinking of them as X, Y, Z, rather thinking about them as the X component, the Y component, and the Z component, then you'll have a vector. So for instance, the position 1, 2, 3, if you want a vector that points from the origin to the point X equals 1, Y equals 2, Z equals 3, then you do 1 minus 0, put that in front of a I hat, 2 minus 0, put that in front of a J hat, and 3 minus 0, put that in front of a K hat, and you'll have that vector. So, all right. Talk to you later, everybody.